Well-posedness of the transport equation and the stochastic perturbation.
So first of all, I would like to thank the organizer for the kind invitation. So this is a joint work on well-posedness for transport equation with Franco Flandoli, which is present, and also Massimiliano Gubinelli from Parigi Dauphine, Franco Flandoli from Pisa. So let me introduce the problem, then I will return on this in a more precise way. But first I want to give a kind of introduction. So I consider first I concentrate on the deterministic transport equation, and then I will show that what is the effect of introducing a stochastic perturbation. So the transport equation, there is a given vector field which we may assume to be continuous and bounded, and we consider a Cauchy problem. T is the time. At time 0 we prescribe a value which is an L infinity function, and so B is continuous and bounded, U0 is in L infinity, and we are looking for a function U depending on time defined on Rd. No? And I think this is a basic equation which appears also in fluid dynamics when U is, for instance, the density of an incompressible fluid, the density in a point x at time t, then you have such kind of equation, but there are also some other applications. So this equation is studied, and the standard framework is, of course, the framework in which B is Lipschitz continuous in x, maybe uniformly in time with a linear growth prescribed. Then if you have this Lipschitzianity, then I think it is standard to study such equation and to prove existence and uniqueness. But I think if B is not Lipschitz, then in general there is no uniqueness of L infinity weak solution for 1. I will be more precise. But now I want to explain that the aim of this talk is to show that if you add a stochastic term, when this is a white noise, there are D independent real valued Brownian motion. If you add this stochastic term, then the Cauchy problem becomes well-posed for any initial datum in L infinity, even if B is only Hölder continuous in x uniformly in t. So if you avoid this, then by asking this kind of this Hölderianity, then you can construct many solutions, but if you add this term, then this situation disappears and there is uniqueness. So the idea is to perturb this deterministic equation with this white noise, no? So introduce this kind of randomness in the equation. I think this randomness is compatible with the equation. The equation will not change, but I think there will be this kind of new regularizing effect. So I think I will write the equation in the blackboard. Okay, this is the equation. I think this seems to be the first example of PDE of interest in fluid dynamics, which become well-posed only under the influence of noise. I think there is a quite general interest to study well-posedness of relevant equation in fluid dynamics, like for instance Euler equation or even Navier-Stokes by stochastic perturbation. Our result is a step in this direction, but we are convinced that for further developments one should have really new ideas. So I will start from the deterministic transport equation. So then there is not the stochastic, there is not here. Forgotten, this is equal to 0. Okay, excuse me. So if B is in L1 lock 0t times Rd with value in Rd, assuming that the divergence of B is also in L1 lock 0t times Rd, and as said before, U0 is an L infinity function. No? So in such situation, we say that a function U depending on time and Rd, so precisely it is a function in L infinity 0t times Rd. It is a weak L infinity solution of this transport equation. If when we integrate against a test function, then you have an identity, the same identity which would be satisfied if U would be a regular solution. So this is a standard definition of weak solution. No? Okay, here there is plus, so in the other part remain plus. So the classical case is the case in which B is Lipschitz continuous uniformly in time with at most a linear growth. And in such case, it is well known existence and uniqueness of L infinity solution. And this is the standard case for the transport equation. So what is the strategy of this approach, which is standard? One solves uniquely the characteristic ODEs in which B is the same with B which is here. So of course in this case there is not this. So starting from S, and due to the fact that B is Lipschitz continuous in X uniformly in T, one can show that there exists a flow associated to this system of ODE. Precisely, if you consider the flow starting at time S from the position X, at time T you will get exactly the unique solution to this ODE. Then, since there is a uniqueness, one can show the flow property starting from S. You go to time U, then you restart from time U, you go to time T, and then it is the same that starting from S to go to T. And also one can show that if you fix S and T, the time, and you look what is the dependence with respect to X, the initial state, then one can get that this map from Rd to Rd are in fact Lipschitz homeomorphism. And so if you think about the transport equation, one can realize that if U maybe is regular, then U is constant along the characteristic, and so you have a candidate for the solution even in an irregular situation. So the candidate, you put here Y, so the candidate to be solution to the transport equation is the initial datum U0 here, no, computed in the inverse of the flow. Starting from 0 at time t, you look the inverse of the flow, no? So taking into account that this is a Lipschitz homeomorphism. This is a candidate, and in fact, one can show that this is in fact a solution, the unique weak solution. So in fact, one can prove that the candidate solution in fact satisfies the weak formulation, and to prove this is not difficult, but one has to use also, of course, some kind of identity. Here it is the determinant of the Jacobian method. This is the Jacobian, yes, of this map, F0T, which is an homeomorphism. So this is the determinant of the Jacobian of the map, no? Computed in X. If you compute this time derivative, then you get an equation, no? Starting diciamo at time t equals 0, there is the condition 1, no? And then I think to verify that this is a weak solution, one has to use such identity. And I think there are not many problems to prove uniqueness. However, the situation changes quite dramatically when you are outside this setting. For instance, even in dimension 1, if you have B which is only either continuous and bounded, then one can prove easily that uniqueness does not hold. And so here I would like maybe to write some elementary example. So if you take in dimension 1, one can take, for instance, this. You can take minimum. Yes, one can take this. Now this is the minimum. R is a fixed constant. This is the minimum between modulus of x and r to the power 3 over 4. And so I think one can show that starting from 0, so this is time, this is x, starting from 0, this is x plus, and this is x minus. So these are the maximal and the minimal solution for the Cauchy problem of the characteristics starting from 0. So roughly speaking, x plus is like T4 for T small, and is like minus T4 for T small. Then I think there is the following situation. If you put here 0, here 0, here 1, here 1, then you have constructed a weak solution to the following equation. Okay. It is not difficult to show that the function defined in this way is in fact a weak solution corresponding to initial datum 0. In fact, roughly speaking, if there are two solutions, then you can put 0 and 1 in some part, and then you immediately construct many weak solutions. So what I will show is that in the stochastic case, this phenomenon will disappear. So in the non-Lipschitz case, which is of course of interest if you think also to the relation to fluid dynamics, when in fact one cannot expect that the velocity field B is regular, so there are problem about regularity of B. So the problem has been studied. I only mentioned two results, but there are also some other results which I have not mentioned. So an important paper outside the Lipschitz situation is the paper by Di-Perna-Lyons. They prove existence and uniqueness of a weak solution when they assume that B is in space is in W11 lock, the Sobolev space, and also there is a kind of integrability in time, and they assume also boundedness and the integrability in time. And moreover, they assume something not on all the derivative of B, but precisely on the divergence, which is the object which appear in the weak formulation. They ask that the divergence is in X is bounded and integrable in T. And so under such assumption, they were able to prove existence and uniqueness of L infinity solution. There are other papers, but I think an important contribution was done by Ambrosio in 2004. He was able to replace this W11 lock condition with a BV lock. No, you ask only that in X the function is bv locally in each compact set, and also to replace condition on the divergence, you take the negative part of the divergence. There are a lot of counterexamples. One, for instance, due to Dupont, but it seems that it's not clear if this is really necessary or not. It is an open problem, even if there are several technical counterexamples around these two results.
Is uniqueness for the PDE equivalent to uniqueness for the ODE always?
I think they are one of the idea of the diurnal ions was first to study the deterministic PDEs, no, to prove existence and uniqueness, and then to use this result to define a kind of flow associated to the ODEs. So they were able to deduce from a PDE result a uniqueness result for the ODEs, given a suitable formulation of the ODEs. Yes. So now I will introduce the stochastic framework in which I will work, but maybe before I, yes. Okay. So the stochastic transport equation, which is in the blackboard, so one can consider the standard Wiener process, no? Each has value in R, so it is a process with value in Rd, defining some stochastic basis. As before, B is in L1 log 0t times Rd with value in Rd. The divergence in L1 log 0t times Rd. And moreover, the initial condition is always in L infinity. And then now I am more precise about the stochastic equation. In fact, this term is intended in Stratonovich sense. No? And then I will say more exactly, but I think these two assumptions will remain for all the talk. So B is in L1 log, and the divergence is also in L1 log. And so initial condition is in L infinity. So what is a weak L infinity solution of the stochastic equation? It is a stochastic process which is in L infinity omega times 0t times Rd, such that when you integrate against a test function, you should get something which allows you to write this stochastic integral. So more precisely, if you integrate against a test function, you ask that this process with value in R as a continuous version, which is also an FT semi-martingale. So this is needed since here it appears a Stratonovich integral, so we ask that this part is a continuous semi-martingale. And then we do exactly the formulation as in the deterministic equation, but simply here there was this gradient which is bad. We put against the test function, and then what we get is a function on S, and we integrate in Stratonovich sense against the Wiener process I. So this is our weak formulation of our equation, and we ask that this is true. P almost surely t is between 0 and capital T. Okay. Of course, one can do a calculation, and one can replace the Stratonovich integral by an Ito integral, and then one has to introduce a correct term. If you think one can show that if this is Ito, then the corrector term, it is like this. Here is the Laplacian against the test function. Okay, this is the formulation of our stochastic equation, and we will show existence and uniqueness in this framework.
Can you show some regularity, the regularity in T, for instance?
We have not checked, but I think if you integrate against theta, there should be the same regularity of trajectory of Brownian motion.
The UI.
Okay, but always one has to integrate against something. Is always a weak property. I mentioned before Hölder spaces. Now I want to be more precise. In fact, we assume that our drift vector fields is in L infinity 0t with time in C alpha b for some alpha. No? This means that each component of the vector field are in this space, which means that they are a Borel function of 0t times Rd with value in R. These are the components. And Hölderianity is in this sense, of course, that you fix t, no, and you get this semi-norm. This should be finite when x and y are in Rd, and also you take the supremum in t, and this should be also finite as well. This is this R function, Borel and bounded, and with this semi-norm finite. This is function in this space. One can show that this is a Banach space. This is the global supremum norm in time and space, and this is this semi-norm. Okay, and what I want to say is also that one can do global parabolic Schauder estimate with these spaces, even for general second-order parabolic equation with unbounded coefficients, and this is a paper we have done with Krylov. But I think for our purposes, we don't need all the full generality. We need a special parabolic Schauder estimate, not the more general one. So I think these are the main results of the paper. No? The main result of the paper are the following. There is a first theorem who say that when you are in dimension 1 and when the divergence is in L1 lock and B is in this Hölder space, which is Hölder in space uniformly in time, then there exists a unique L infinity solution. But here it is only for the dimension 1. No? And then there are two theorems which are true in any dimension. No? And the second theorem says the following. You ask Hölderianity, but alpha greater than 1 over 2. No? And then you ask a small integrability condition on the divergence, which is almost necessary to give the weak formulation. So roughly speaking, you only ask Hölderianity, but with alpha greater than 1 over 2. And then you get there exists a unique L infinity solution on this. And then there is also, we can also treat the critical case for us, which is the case in which alpha is less than 1 over 2. And in this case, when alpha is small, then we have to impose a global integrability condition on the divergence. Remember that also in the paper by the Pernal-Lyons, they ask a global integrability condition on the divergence. No? Precisely, they ask the divergence of B should be in L1 here, and here there should be L infinity. No? So they ask something of global, and in this critical case, we should ask also something different, but always global as far as the divergence is concerned. And this is required for some P greater than 2. So in this critical case, we have to ask this kind of global condition for some P greater than 2. Okay. I think one can also, maybe to simplify a bit the exposition, one can also think that B does not depend on time. Then it is more easy to understand the result. Divergence B should be in LP, this should be B should be in C alpha. It is more easy to remember if you don't consider the dependence on time. So what is the strategy of the proof? So we first look to some stochastic differential equation with no regular coefficients. Since the idea, our approach was trying to follow the method of the characteristic, no, and try to see if there is some help from the noise, and then to start with this. And so we look for a stochastic differential equation with no regular coefficients in Rd, and B is our B, so which is roughly speaking Hölder continuous, no? And then here there is a standard Wiener process with value in Rd, and so we look for this equation. No? B is Hölder, so it is a singular coefficients. No? Of course, there are strong solutions if B is Lipschitz by fixed point method, but there are also other results in irregular situation. I think there is also a paper by Zvonkin in dimension 1, and then there is this paper by Veretennikov, who used also this Zvonkin method. Veretennikov was able to prove the following remarkable result. If B is Borel and bounded, then he was able to prove uniqueness of strong solution for this equation. It is crucial for his approach that here you don't have a degenerate noise, since the noise should help. If you Veretennikov put even here some multiplicative noise, but it is non-degenerate multiplicative noise, so it is crucial. Otherwise, he cannot use analytic result, and he cannot obtain uniqueness of strong solution. Then there is another paper by Krylov-Röckner. They prove strong uniqueness when B is in some LP-LQ space, in time and space. They have this condition that the dimension over P plus 2 over Q should be less than 1. And then, of course, I mean strong uniqueness of a global solution. So one has to impose also some non-explosion condition to have this, since I am speaking about a global solution defined for any time. There is also an interesting result by Devi. He improved the result of Veretennikov by proving that almost surely there is a unique solution, even not adapted for almost surely Brownian path. So this result showed that the noise, in fact, regularized. If you add this to this equation, then you obtain a regularizing effect. And we had a result.
In fact, the paper of Zvonkin is stated in dimension D. Maybe it's not easy to interpret this, but at least they...
No, I wanted to say that here there should be Zvonkin paper, which is in dimension 1. And Veretennikov did in dimension.
If you read the paper of Zvonkin, I mean, at least it states some results in dimension D. Then,
okay.
Of course, I try to understand, but it's not.
Okay, so yes, one has to precise this. In any case, okay, va bene. We need something more than the strong uniqueness of the stochastic equation. So we need a flow to prove our uniqueness result for the PDE. And so I recall the definition of stochastic flow of diffeomorphism. No? FST is the complemented sigma algebra generated by the increment of Wiener process, no? When you have R and U between S and T. No? And then we look at the definition of stochastic flow as it is in lecture notes by Kunita. So a stochastic flow diffeomorphism, C1 plus alpha log, it will be our situation, no? On the stochastic basis, associated to the stochastic differential equation with additive noise, I've written before, is a map STX omega, defined from S and T. We fix capital T, no, S and T value, X in Rd, omega in omega with value in Rd. And then one has to ask that if you look to this quantity, to the flow STX, this gives exactly the solution to our equation. I remember I rewrite the equation before. Yes, this equation starting from X, this was the equation. Yes. Yes, and then as in the setting of Lipschitzianity, one will ask that P almost surely phi st is a diffeomorphism, and also that this function, this is the inverse function, this is the Jacobian matrix, the Jacobian matrix of the inverse are continuous in STX. Since we are interested in C1 plus alpha, we will ask C alpha log uniform in ST. And then we ask, of course, the flow property, P almost surely. It is exactly as in the previous standard framework. We ask this P almost surely, Fss equal x. This is the definition of the stochastic flow from Kunita. And then Kunita proved also the following result. I use my notation, so he asked that the drift is C1 plus alpha b. No, it is bounded. It is asked this uniformly in time. No? And also sigma is in the same situation, C1 plus alpha b uniformly in time if there is also time. And then I think he proved that there exists C1 plus alpha prime stochastic flow when alpha prime is less than alpha. No? And this is a point for us. In fact, later I will show that the fact that here we cannot put alpha prime equal alpha is what stop us to reach the level 1 over 2. And so we have to take our Eulerianity strictly greater than 1 over 2. Exactly this is the point. I will show this later. And but then what we did about the previous equation concerning the flow. So we assume that B is in L infinity with value in C alpha. No? And then we prove the following two theorems. We prove pathwise uniqueness, no? That there exists a strong uniqueness, there exists a unique continuous adaptive solution. I think this was already known by Veretenniko, but we use, I think, a variant of this method, a variant of Zonkin method, and so we prove directly also this result. And then there is this new part. We prove, in fact, that there exists a stochastic flow of diffeomorphism, and this stochastic flow is of class C1 plus alpha prime log for any alpha prime less than alpha. Alpha was the parameter of Eulerianity of B in our initial equation. So this is our new result. I want to give an idea how we get this result. No? I want to give an idea about this. We use something which we call an Ito-Tanaka trick. So this is the equation. There is additive noise, so one can write in this way. I explained the idea in the easier case in which B does not depend on T. No. So this is to explain the idea. And then I think here there is dependent on X, okay? And we want to show that at least something, but also at least that with respect to X there is smoothness, no? And so the idea is forget for a moment this and write an Ito formula, no? We write an Ito formula with a function g, no? Which is regular enough. And then if you compare this new formula with the previous one, you see that if it happens that this function g is Lg equal to B, roughly speaking, more precisely this is the relation, there is a parameter lambda inside, then this means that if this is equal to this, roughly speaking, you can replace this by all this term. No? And this reminds us the trick of Tanaka to write Ito formula for a convex function. And so we call it Ito-Tanaka trick. But precisely, you look to solution to this equation on RD. Lambda is a parameter. No? You take a parameter lambda positive. You consider these are independent elliptic equation in RD. There is a Schauder theory for this. B is bounded and Hölder continuous, standard theory. And so one can find solution GI, which are in C2 plus alpha, no, B. And so with this function, in fact, we can rewrite this in terms of this. So since this has been replaced by I think using this identity, here you can put minus, so you can arrange the minus, you can arrange lambda, and so finally this identity will become this identity with this regular function g. But then g has two derivatives more than b, and so since it has two derivatives more, and also you know that this gradient is this derivative is Lipschitz continuous. From this you get immediately strong uniqueness, but you can get even more with this approach. No? With this approach, one can define the x plus gx. No? One can rewrite the equation in the following way. No? And then I think these are the elliptic estimate I have mentioned. So these depend on lambda. No? I think they are C2 plus alpha, but also I think it is important that one can choose a parameter lambda in order that the gradient of G lambda, this is the supremum norm in RD, is small than maybe 1 over 2, no? Since this is part of the classical elliptic estimates. If you choose this lambda big enough, then you have this auxiliary function, which is not only C2 plus alpha, but it is also C2 plus alpha diffeomorphism. No? And then if you take a solution from the initial equation, you take this psi, you take another condition, and you get another equation. But this is a good equation in the framework of Kunita. Since if you do the calculation, there are diffusion metric depending on the diffeomorphism. There is a drift depending on the diffeomorphism. One can check that everything satisfies this assumption. And this assumption allows to apply the Kunita technique, which is based on the Kolmogorov test. And one can prove that there exists a C1 plus alpha primo log stochastic flow, no? So with the equation. And so I think now we have two equations. We can pass from one equation to the other equation by using Ito formula. No? So we will get a nice property for our bad equation for a property for this nice equation. And in fact, if this is the flow of Kunita, we can come back and get a flow for our initial equation. So one can check, in fact, that if this is the flow of Kunita, you apply our diffeomorphism, no? Depending on lambda, but lambda now is fixed, and one can get that this is a flow for our initial equation. So we have, in fact, a flow for our initial equation. Okay. So there is also an equation for the derivative of the flow which we can write. Yeah, okay. Now, after this part about the flow, I can come back to our stochastic transport equation, since now I can profit of the existence of a flow. So first, one can concern about existence. So there is a candidate to be a weak solution, no? And in fact, one can prove that in all the three theorems I have mentioned, this is in fact a weak solution. And this is not difficult. One can approximate, in fact, this flow with some regular flow corresponding to regular B, no? Do the integration of the weak formulation, and then pass to the limit as epsilon tends to 0. One can pass to this limit. So this is a weak solution. I will concentrate a bit on uniqueness. I try to give some idea, not maybe all the details, but some idea. So, of course, we start by looking to the paper by the Pernal ions. No? But there is an important difference that they don't have the flow, no? In fact. As he mentioned, that they construct the flow only after solving the PDEs. So they have to work with commutator. Commutator are the following type. So you take V is a vector field in L1 lock, the divergence in L1 lock, G is in L infinity. So one can first define this distribution, but then the main point is this commutator R epsilon Vg. It is a smooth function. It is, you take v times gradient of g, defined here, you convoluted against this test function minus v multiplied by this. So how to remember this commutator? What is this commutator? This commutator appears exactly as an error term of the transport equation. This is easy to remember. In fact, I think if you take the transport equation, no, and you convolute, no, each part of your transport equation, no, you convolute, and then you want to write the transport equation in terms of u epsilon, no, you have to put an error term. You have an error term. The error term is exactly this commutator. Okay. And then I think, in fact, the result of the Pernalions, what they prove in fact that assuming that you have a vector field which is in W11 loc, assume that you have a function g in L infinity, they prove that if you consider this commutator strongly converges to 0 in L1 loc. And I think this was the crucial point, since they have such an equation, no? And I think if you pass to the limit, you don't see immediately that u is so this should tend to 0 by this lemma, but then you don't see exactly uniqueness. But one has to do some manipulation of the equation. For instance, one has to ask instead of u epsilon, you should ask u epsilon square. No, you should do some manipulation. You will get here maybe multiplied by u epsilon, but you have a strong convergence. No, and so at the end, with this good result working at the level of the PDEs, one can show that in fact u epsilon tends to 0. Okay, but this gives uniqueness. Since you start from a solution u, you make smooth, but you make convoluted, you get u epsilon, and then u epsilon tends to 0. This means that you are started from 0. So, but I think it's not immediate how to, but this is the crucial point to get uniqueness for this equation. So we don't follow this approach. We don't follow this approach since we want to improve deterministic result. If we follow the previous approach, we will not improve the deterministic result. And so we have this idea. It is not rigorous, but gives the idea of what one has to do, at least in our situation, to get the more information we have. So we use our flow, and if you use the flow, again you take a weak solution, you consider u epsilon, you consider a solution u epsilon on the flow. This is the flow starting from 0. And then this is not possible to do this derivation since the trajectory are not differential, but assume that we can do this derivation to have the idea. Then you get this, and you get this in Stratonovich sense. No? And then exactly what happens? It happens that you get exactly the error term as before, since this is the commutator of so has to be more precise. So you get the derivative of this, but this solve, I think, this equation. No, okay. Not exactly. Solve this equation plus an error term, which is the commutator. Okay. You put everything on the other part, there is sinus minus, no? And so this is why there is a cancellation. And what remains is the error term, which is the commutator. Okay. I think you agree that. Yes. So differently with respect to the Pernalions, we have the following situation. We have a solution, we have convoluted in space, no? We minus initial condition convoluted, and this is equal to this. We have heuristically, is not proved rigorously, we have this identity. And so we are looking to exactly to prove this identity, and then to do the second step. So to pass to the limit here and to prove that this tends to 0. Then what will appear is that this will tend to 0, and roughly speaking, this would mean that u epsilon tends to 0, and so 0 is the unique solution. So this is what we want to establish rigorously, since this is not rigorous. But I think first I should mention this lemma, which we have motivated by the previous formula, which I will establish in a moment. We are interested in variant of the commutator lemma, in which there is also a diffeomorphism involved. No? Since there is, as I said before, since we have this, we want to have commutator applied. Forget for a moment this integral in t. We have commutator applied to a diffeomorphism, and we want to understand what happens when epsilon tends to 0. And so we prove the following lemma. Assume that phi is in C1 diffeomorphism. Assume that V is in L infinity lock, diverges in L1 lock. So it is similar to what was before. But now there is a diffeomorphism, and you consider the commutator, no? Against a test function, but the commutator which has inside a diffeomorphism. No? And I think what we prove is that if there are such assumption, we have such estimates. Here there is rho, here there is also, there should be the gradient of rho. So what we prove is not that this quantity converge strongly in L1 lock, but converge against a test function in to 0. No? And this is what we would like to use. No? Commutator with inside the diffeomorphism converge in a distributional sense. Okay, now one can be more rigorous. So we want to prove uniqueness of L infinity solution. So we start from 0 initial datum, and we want to prove that 0 is the unique solution. So U is such solution. No? We choose a test function. We define convolution in the space. No? And I think what we get by the definition of weak solution is this expression. One can check this calculation. And then what we do, we put instead of y our flow, no? And we look to what happens. Our dream is to get the formula which was written before in an heuristical way. I think there is a version of Ito-Kunita-Wenzel formula. One can in fact prove exactly what happens if you apply to our U epsilon, which is a random field, you apply the flow, and one can compute exactly what happens. No? And finally, after some calculation, we get exactly the formula we have in mind. Exactly. P almost surely, I think. And so we have some chance to get uniqueness if you are able to show that this tends to 0. Since if this tends to 0, this tends to 0 against a function in a weak sense. Okay, there is the diffeomorphism inside, but roughly speaking, if U with inside the diffeomorphism is 0, it is 0 also the function without the diffeomorphism. So one has to do that this tends to 0. And this is exactly what we did. But here no, there is something more precise, so one can change variable. This is the Jacobian, no? And then, yes, one can, so this is to show that this against test function converge to U against test function. And this is more rigorous to say that if you get that this tends to 0, this means that U is identically 0. This is more rigorous. Okay, but then I think we have this identity, as I said before, crucial to understand that this should tend to 0. This is the point. So in the case in which alpha is greater than 1 over 2, we can solve the problem of passing to the limit by applying another variant of the commutator lemma, in which we more or less ask something more about the vector field in the commutator. No, we ask not in the previous commutator lemma we ask only that this was bounded, but here we profit of our assumption of the reality and we ask this, and then we get convergence. No, but the problem of this is that one need, I think, this should be C alpha, and this, the Jacobian of the flow should be C1 minus alpha. So roughly speaking, when you want to apply to our situation, so V is our drift B, no? G is our bounded solution U, and phi is the flow, no? And so what is our problem? If V, which is B, is C alpha with alpha small, then you should get, this is roughly speaking the derivative of the flow in C1 alpha with, so in a Hilbert space with a high exponent, and we don't have this. Roughly speaking, we have, then this and this are the same. Not exactly, since there is a strictly. So finally, if alpha is 1 over 2, we don't have that this is 1 over 2, and so the case 1 over 2 is not covered. If alpha is greater than 1 over 2, this is 1 over 2, and this works. So the critical case require more argument. In fact, so in this case we cannot profit, at least we don't know how to profit from the fact that B is Hilbert continuous of exponent alpha, and the Jacobian of the flow is Hilbert continuous of exponent alpha prime strictly less than alpha. We don't know how to profit from this. And so we try to get some kind of weak integrability of the Jacobian of the flow. And so we try to show that the Jacobian of the flow, it is in a Sobolev space. No? A Sobolev space in space, and also there is a integral in time. Okay. If we get this, then we can apply the first commutator lemma we have proved, and we can conclude uniqueness. So we need that in space the Jacobian should be in W11. So roughly speaking, the flow should be in W2 to 1 lock. Okay. And the proof of this new regularity result for the Jacobian is quite involved. We need this for alpha less or equal than 1 over 2, but probably it is also some interest independently on this. But our basic observation is that if you take the Jacobian, you take the logarithm, it solve it is given by the integral of the divergence of B. So this means that if you are able to prove that this quantity is in fact in the Sobolev space, then you have done. Since here there is a nice function applied to the Jacobian. The Jacobian is never zero in a compact set, so it is everything is all information are here. And to show that in fact as a function of x, this is in the Sobolev space, we use again the Ito Tanaka trick. But to use this, one has to ask some regularity on the divergence. We don't need to ask the reality, since now we need less on the Jacobian. So we only ask that the divergence is in LP. And then we introduce, before there was the elliptic problem. Now we cannot avoid the Cauchy problem. we cannot avoid a parabolic problem. In fact, we consider this parabolic problem. And by our assumption on the divergence, recall that B is also bounded from the beginning. There is one can have this. This is a standard result in parabolic equation. And so, what it means? It means that this identity say that when you look to an Ito formula for this quantity, no, you can replace all this part in the Ito formula with the divergence. Then you isolate the divergence, and you get the divergence equal to something else. But then you see that you understand that what is here in X is a nice property, since here in X you only see you see very few, since divergence of B is simply in LP. But here this gradient is in a Sobolev space, in space, so this F is more regular than, even the gradient of F is more regular than the divergence of F. So one can profit of this. This is formally, to be more precise, one has to do approximate B by B epsilon, then the flow is approximated, and one has to find estimates which are independent on epsilon in order to get our result. But this is now a formal explanation. So I think I have almost finished. So I think I will finish by a counterexample. No? So maybe I mentioned that one of the problems to extend our result to the case in which B is random, no, is shown by this example. No? If B is random, take for instance the square root, X is in R, you take X minus WT, you take the modulus, and you look to this equation. Then I think the problem is that one can do the usual change of solution of unknown function when there is additive noise, and since this is random, you get a very bad equation. And so this shows that for such a transport equation, when here B0 is maybe square root of X, you will there are many solutions, and we don't know how to, so we cannot of course expect a uniqueness for such equation. So this means, for instance, that if you try to apply this maybe to Euler equation, you have a problem, since of course you will have for instance U multiplied by the gradient of U, roughly speaking. U is random, so one has first to understand this case, at least, if you want to. Maybe one has to change the stochastic perturbation in the nonlinear case, but this is a challenging problem, and we are working with Max and Franco on this. I think I wanted to say something more, but maybe it is. So we have also some result on the flow for more general equation, in which we may have also B, which is unbounded and Hölder continuous. And to treat this flow property, we need some new regularity result, and I think we need a regularity result for elliptic equation in which the datum here is unbounded, and also the drift term is unbounded. But I think I have said much, so thank you for your attention.
So any questions, comments?
So just naively, if coming back to the initial problem, deterministic in fact, but of course in the problem with relation in the stochastic case. So if instead of having a dW, so a white noise there in time, so one could imagine maybe that with some pathwise techniques, one could do something, I don't know, with a Hölder continuous path. So if you have a a sort of Young integral there. So in the sense that, so because of this I was asking if you have some order continuity with respect to t, so one could expect, at least formally, some calculations.
This we have to discuss. I don't know exactly. You mentioned Young integral.
Young integral,
Yes.
in the sense that you have it's a generalization of bounded variation integral. So instead of having a bounded variation function, you have a order continuous function, and then you have to Young, yes. And then you, of course, you expect that the integrand is also Young with some regularity. At least formally, one could maybe imagine that.
Yes,
But
maybe, but
of course,
to prove uniqueness.
no. The uniqueness is
to improve the regularity of the
incredible.
solution. To prove the regularity.
no, just to replace other types, because you consider bounded variation case and so on.
I think there is also
consider order case.
Yes, I think this we should talk. But in the paper there is also a formulation of the equation, which is quite long to write, in which does not appear the Stratonovich integral. In the paper we have in appendix. So maybe this is related to your question. But
In
we
this
should
case,
discuss.
all the integrals are the same.
We should. Yes, thank you.
Any other question? Yes.
So if you had a smooth approximation of the Brownian motion, instead of Brownian motion, you don't have uniqueness for that, or do you? It's along the question he's asking you. If instead of putting dw, I put a smooth approximation to dw.
If we have a uniqueness for this approximation.
So you don't have stability in some sense. You don't pass to the limit. You cannot pass to the limit.
I should think about this interesting question. My feeling is that we don't have. So.
Because in essence, what you are also doing is you are solving the Lyon's problem for very special B, because you can always absorb the Brownian motion inside the B. And so it's like solving a transport equation in the Lyon's class. I mean, like the Lyon's equation, not with the same assumptions, where now the B is Bx minus Wt comma T.
Mm-hmm.
And somehow for that equation, you're proving uniqueness.
Yes.
I mean, that's consistent with all the stuff Lyons and I did on the Hamilton-Jacobi equations, where we are absorbing the stochastic part inside the deterministic thing. And so your theory says that if I look at Vt plus B of x minus Wt comma T dot dw dot V, this equation has a unique solution. So there must be something more
general than this white noise.
Because then in that case, if I put an approximation of the Brownian motion at the level of the deterministic equation with random coefficients, there is some stability. So if I have a W epsilon there inside the B of x minus W epsilon T, forget the extra dependence on T, then the coefficients converge uniformly. If I have a pathwise approximation. So there must be something going on there that...
But B here is only C alpha.
I understand, but for B of, let's forget the T dependence on B. For B of the form x minus Wt, you are proving uniqueness with B in your class, C alpha, whatever it is. So for that particular B, you are proving uniqueness. So I'm asking, okay, if the W there is not Brownian motion, is a W epsilon that converges pointwise to Brownian, or uniformly to Brownian motion.
I don't know.
We included a Wong-Zakai result in the paper, but for the approximant, we don't have uniqueness, because under C alpha we cannot say unique. For any solution of the approximant problem, we have a Wong-Zakai result.
Other questions? I have a question. Maybe you wanted to explain it at the very end. But what happens if you do a perturbation which is a bit different, by, not with constant white noise, but well, you can put coefficients depending on x. Then I understand you will need absolutely to have ellipticity. But so it will be.
I think
more or less the
my thing would be the same. If there is a multiplicative noise which is non-degenerate, I think we could do all the result. I think, we could do all the result, but I think sigma should be a bit regular. Should be C1 plus alpha, since when I pass to the Kunita type equation, I should take into account that there is now sigma also inside. So you are right. We need this multiplicative noise, non-degenerate, and with some C1 plus epsilon. I think it should be okay. We could repeat the method. Yes.
So basically, can we say that the regularity you get for the solution of the PDE, I mean the PDE in which the PDE associated with the elliptic PDE, I mean the one which is associated with the W, actually is inherited by the transport equation?
If we did
that, for example, this PDE, the solution would be.
I think in the assumption we said before, there should be, yes. The method should work.
What does this equation become if you write it in Ito rather than Stratonovich?
There should be, it is here, I think.
Faster if you write it.
Yeah, but it is a bit involved. I think it is here. So so this would become Ito integral. Then one has to write the variation between this process and this to calculate the variation. Roughly speaking, you should put this as a test function, and finally you get Ito plus this deterministic. This is the, yes, so if you want to write in this, you should put the Laplacian against u.
Right. No, it's okay.
Okay.
Right, so, well, I think we need time for tea, so let's thank our speaker.